Brilliant. What an absolutely brilliant session. Thank you so much, Alistair, and all of you panelists. That was absolutely insightful. Thank you.
Always one of the highlights, actually, is list of conversation. Every year we get a different topic from you and new insights. So thank you again. And what have we got coming up, Fran?
We have got so much still to come on Mars Day 23. So going into the afternoon, we are going to be having some panel sessions where we look at some hidden heroes who are working in science, technology, engineering and maths all around these space missions. And then we have a short break. And then after that break, we meet some of our international stars. And we go over to JPL over in California. We also live link up with Washington, D.C. and Wimbledon, where we will learn more about our guest planet, Jupiter. And then we are going to go over to French Guiana. But for the next hour, well, we're 5 minutes away from, oh, I'm so excited. It's 5 minutes away from Mars Hour, but we can't start it before. We're going to keep on. Oh, we've got so much coming up because that is coming up at 11, but we won't start just before. Before that, we will give some shout outs about things that have been going on at social media. And if you are taking part in Mars Day, please do tweet us at @0_UK and use the hashtag Mars Day 23, but from 11 you can use the hashtag Mars Hour 23. And so we've had people hashtagging us. We have had a Maze Lab who are doing brilliant stuff with us. They were running our primary school sessions in the morning, and they're also taking place this afternoon as well. We have had some primary schools joining us. We've got some Green Street Green Primary School have tweeted that they're happy about Mars Hour and Mars Day. And here we have Beddington Station Primary, who have been really enjoying the Moon and Mars show. That has been going down a storm. There is so much going on today, isn't there?
And actually, you have a few minutes left. So if you haven't quite prepared your Mars Hour activities, you have about 3 minutes to give it a bit of thought.
2 minutes, 2 minutes.
You go on the website, marsday.org.uk, and you can find resources there. Even if you haven't prepared anything yet, there's plenty there. You can just go onto that website and then pick up some resources and find some activities to run at home, with your school, with your community.
And the thing is, Mars Hour, you might not know this, but it's not going to be an Earth hour long. It's going to be a Mars hour long. So it's not going to run for 60 minutes. Instead, it is going to run for, are you ready for this? 1 hour, 1 minute and 36.968 seconds. And that is the equivalent to an hour that is on Mars.
Okay, we'll make sure we time that exactly then, Fran.
We'll see how we go. I'm not sure my watch is that precise.
It looks like it might be 11 o'clock though.
We are coming up very shortly. I think, yes, let's start it.
Well, in that case, we need to introduce our first guest, and we are so excited to be speaking today with Tim Peake. Britain's astronaut went to space recently, can tell us all about his adventures and activities. Tim, thank you so much for joining us. Well, last year you were with us and we were doing activities, but thank you for coming back and joining us again.
Hi, Susie. Hi, Frank. Great to be back again. Great to see you and great to be here for Mars Hour.
Thank you. I think pretty much everyone watching is going to know who you are, but maybe just to start off, you could tell us a little bit about your career in space and the particular mission that you were involved with.
Sure. So I joined the European Space Agency in 2008, and I was part of a group of 6 astronauts who were selected back then. And I had the opportunity to fly to the International Space Station in 2015, actually on this rocket behind me that you see there. So that was me, Tim Kopra, Yuri Malenchenko, sitting on top of that as we flew to the ISS and spent 6 months living and working on the space station. Space station is just such an incredible structure. It's our kind of orbiting laboratory that we have at the moment. It's been up there for over 20 years now, and we just run a continual sequence of scientific experiments that are going on. And so as a crew member, you join into that process and you run whatever science experiments need to be done. So it was absolutely fascinating to be part of that process. And I also had the opportunity to do a spacewalk because it is old, the space station, so bits of it occasionally break, need repairing. And we also do experiments outside the space station as well. So we had to go outside and repair one of the solar panels during that. So an absolutely fascinating mission and just gave me a real insight into what it takes to actually live and work in space.
It sounds like you got involved in all sorts of different experiments up there. You kind of became a little bit of an expert in lots of different areas of science and technology then. Maybe talk to us a bit about some of your favourite experiments or activities that you were asked to carry out.
You do. You have to be a bit of a jack of all trades, really. And the training process before you go to space is about 4 years for your first mission. There is just so much to learn because you have to learn about the spacecraft you're going to fly in. You have to learn all about the ISS. You have to learn about spacewalking, about robotic arm, how to capture visiting cargo vehicles and dock them. And really, actually, the science is one of the later things we learn about so that it's fresher in our minds. And also, we don't know what science experiments are going to be run until quite late on. But when we get our science package, then we'll be traveling around to Japan and Canada and Europe as well, because all of these science experiments are being run by different laboratories around the world. I did a fascinating experiment which involved actually going to the airlock, which we normally only use for a spacewalk, and we had to drop the pressure, and that was looking at airway inflammation, trying to help people who suffer with asthma back down here on Earth, investigating why the airway becomes more inflamed and how we can find new techniques, new drugs, new solutions for helping asthma sufferers. But we're looking into a lot of it, the life sciences, about the aging process, because the human body, when you go into weightlessness, you actually go through a rapid aging process, which is not very pleasant at times. But and that's why we kind of do it on relatively young, fit people. It would be pretty unfair to do that to the elderly. But what we're doing is we're learning about the aging process so that we can discover new ways of dealing with things like osteoporosis, things like cardiovascular disease, things like immune system deficiencies. And that's great because it's an environment where we could do it very controlled. And when we come back to Earth, actually, most of those changes, they reverse themselves. So we do get back to full sort of fitness and health. And that aging process, thankfully, reverses, although you wouldn't know it looking at the wrinkles on my face at the moment.
21 in a day. But tell me about that. I mean, in essence, you're the experiment for some of these. You, the humans that are up there. It's not just other experiments that you're doing or carrying out. You yourselves are part of the experiment then in that environment.
That's right. Yeah, we do lots of experiments with things like material science, and where we're just running experiments that we don't have a huge amount of human input to. But then you're absolutely right. The life science experiments are the ones that the astronauts are very much the guinea pigs, if you like, and we're being studied. So we spend a lot of time doing things like blood draws, things like ultrasound scans, visual eyesight tests and sonometry, looking at intracranial pressure, looking at muscle atrophy, bone atrophy, all of these kind of things. So it is quite incredible. You do get very used to sticking needles into yourself, as we have to do blood draws about once a week.
And by atrophy, you sort of mean deterioration, yes?
That's right, yes, a deterioration. And it's fascinating because we realize this happens in weightlessness because of the early astronauts and cosmonauts who are flying for long periods in space, were coming back sometimes with up to 20% less muscle mass and bone density. And clearly that's quite a problem. That's quite damaging. And actually you have a danger of fracturing your bones even when your bone density is that much reduced. And it will recover. You can recover that, but you have to be very, very careful. So we would rather not lose that muscle mass. We'd rather not lose that bone density. And we've discovered that it's actually exercise is one of the best ways of doing it. And it's the interaction between the muscle and the bone. Every time you look at a muscle on your body and you feel where that muscle joins onto the bone, it's that interaction there, the muscle-bone interaction around the ligaments. That's what helps to promote bone growth and helps promote muscle growth as well. So by exercising in space, we try and stop the reduction of that muscle mass and bone density loss.
I think people around the country were just all feeling their muscles. I was trying not to. And I will say, if you are watching online, you can put your own questions to Tim. So do use the hashtag MarsHour23 and do send them into the chat as well. And we can propose your questions to Tim.
I think actually, from memory, didn't you run the London Marathon when you were on the international stage? Talking about exercise in space.
I thought that might be a good idea, running the London Marathon, because we were doing so much exercise training anyway. I thought, well, great opportunity to do it. So I did run the marathon. Yes, yeah.
Have you done a marathon before?
It was a little bit more painful than I thought it was going to be.
I guess there are some challenges as you're bouncing up and down on the treadmill to deal with.
Yeah. I mean, the treadmill, it's a great device. It's designed to be used for a short period of time, though. It uses this bungee system. So that bungee replicates our body weight. So it's like putting on a rucksack, really, like wearing your own body weight on a rucksack. And that's what keeps you pinned to the treadmill. And that's fine for 20 minutes, 30 minutes. But after an hour, it kind of cuts the blood circulation off at your arms. So I was on that thing for 3.5 hours that morning, and my arms went pretty numb.
I bet you were wishing you could be running faster to get that over quicker. So.
Yeah, it makes you feel, even in space, you can run a marathon faster than I can. That's impressive.
Don't feel bad. I think, one of the things you touched on, which is quite interesting, is that there's quite a lot of experiments that happen on the ISS, on the International Space Station, that have quite big and profound conclusions for us living on the Earth. It's not just experiments to investigate things that happen in space, for example, but actually these things are important for understanding more about our life. Things like recycling on the ISS as well, being able to recycle materials, all that kind of thing. So tell us a little bit about some of the things that you did up there that maybe have already affected research here on the Earth.
Absolutely, you're absolutely right, Susie. Yes, so much of what we do in terms of science on board the space station is actually looking back towards Earth. There is an element of doing experiments to help us to explore further into the solar system in the future, but probably about 80 to 90% of all the science is focused back here on Earth. Some of the latest experiments that are becoming really successful are actually to create new drugs for diseases like Huntington's disease and Parkinson's disease, many people will have heard of, and motor neurone disease. Why is space good for that? Well, the reason is the drug companies, to create a new drug, you have to look at the disease that causes it. And we have disease-causing proteins. So you grow these protein crystals here on Earth, and then you study those protein crystals and you try and get a drug to wrap around it like a 3D jigsaw puzzle. But here on Earth, you can't really grow very good protein crystals because of gravity and sedimentation. It crushes them down. Any 3D structure struggles to grow in a gravity environment. So in a weightless environment, you can grow really good 3D structures. So protein crystals, very large, very pure. We then bring those protein crystals back to Earth, and we could develop very, very good drugs. And that means low dosage rates for patients. It means very few side effects for patients. And this is a really rapidly growing area of research on the ISS. And just like protein crystals, well, you can start to grow live organs, for example. Any 3D structure that's fragile in weightlessness is going to be a great candidate for study and research on board the ISS. Metal alloys, they crystallize in a similar way, so we can grow metal alloys in space that we can't make on Earth, and that's crazy. You can bring back, metal alloys that have properties you wouldn't believe here on Earth: elastic, light, strong. And so this is where we're going in the future. We could end up producing a lot of material in space, in weightlessness, and then bringing it back to Earth and then applying it to reduce the weight of our aircraft, make them more fuel efficient, which makes them obviously cleaner and greener.
Yeah, the experiments that you were doing basically are sort of seeding the commercialization of near-Earth space for manufacturing, which I think is fascinating.
And there's so much going on, it's not just about that exploration, and there's so many different jobs that can feed into it, and also different jobs that can feed into the science in it and then feed off the science that comes from it. And it's absolutely fascinating, Tim, but I do have to leave you in Susie's capable hands because there is so much going on at HQ, but I will see you guys later.
Yes, we'll catch up with you in a second. Fran, a couple more questions for you, Tim, actually. One of my favorite videos of you when you're up on the ISS is you are crunched into a ball and somebody is spinning you. And you start spinning, and anyone watching, you must find this video. I'm sure you can find it on YouTube or somewhere. Just watching you spin and spin and spin and faster and faster. And I get a little bit motion sickness, not terribly, but, a little bit. And just watching you made me feel unwell. What were you trying to do there? What was that all about?
Oh, that was a fun morning actually, and it came about by surprise because I was doing a task that morning where we have to try and squeeze air out of our water containers. We have some emergency water on board the space station, and over time they get air pockets. And the way to squeeze the air out is you have to spin yourself around, and that way all the water goes away from you, and the air pocket stays close to you, and you can then squeeze the bag like a bagpipe and let the air out. And I was doing this for about an hour and a half with all of our water. And I realized I'd been spinning around for an hour and a half and I hadn't felt dizzy at all. I thought, this is unusual. If I was on Earth, I'd probably be feeling a bit unwell by now. So I said to Tim Coper, let's do a quick experiment. And I set the camera up and said, just spin me around. And I want to see if I can make myself dizzy. And he did. And I was moving my head all over the place and going faster and faster. And then he stopped me very rapidly and absolutely no dizziness at all. And it was just for a little bit of fun at the time. And then when we sent this video down, Mission Control looked at it and thought, this is really interesting. I think we need to do a medical study on dizziness in space and what's happening with the vestibular system to allow that to happen.
Excellent. See, it looked fun just watching it, but there's a medical thing there underlying that. Maybe not intentionally, but I'm sure people are going to be looking into that moving forwards. You also did a lot of outreach, a lot of activities kind of designed for helping people understand the environment, helping people think about living and working in space. And you had your own sort of little mission, Principia. Can you talk to us a little bit about that?
Yes, I mean, it was so important to use an opportunity like a spaceflight to try and engage with as many people as possible. And space is such an exciting area to do that in. There is so much happening at the moment, so much going to be happening in the next 5 years. So we really wanted to reach out to as many schools and young people as possible. And we ended up, having 2 million people follow the mission and join in with some of these research programs that we were doing. And for me, that was fascinating. I loved it. And it was really rewarding because, I think to try and help to inspire young people to look at science, look at engineering, look at technology in a different way is really important. We're surrounded by tech today. Any future career is going to have an element of science and technology involved in it. So I think the more that people engage with that at a young age, then the better their opportunities will be for the future.
And it wasn't just the young people. I have to say, when you launched, we had a party at the university and we made Tim Peake shaped cookies. We made cookies in the shape of you and we iced them and we celebrated your launch. So it wasn't just the young people, the rest of us were having fun too. We've talked a bit about, I'm going to send you a photo actually, I think I've got one. We talked a little bit about your mission and what you were doing, but I guess the job of an astronaut, it doesn't finish when you come back to Earth again, does it? So tell us a bit about what happens when you come back and what you've been doing since you came back from your mission.
Yes, there are various phases you go through. So when you first come back, you're still that guinea pig, that life science experiment. And so now the scientists are looking at all the changes that happen to your body very, very quickly as you come into a gravity environment. So the first 6 months back on Earth are busy with experiments, with debriefs, and then you go into a position where you help your colleagues because your memory of space is very fresh, your knowledge of what we're doing in the ISS is very valuable. So you feed that back into the process, and I became head of astronaut operations for 2 years immediately after the mission so that I could then really help my colleagues who had missions coming up. And of course, it's important to be an ambassador for space as well. So there's an element there of going around and talking to people and educating people about what we're doing. And that's similarly what I'm still doing today to some degree. And also working with not just the European Space Agency, but the UK Space Agency in particular, on both outreach programs, but also looking at our industry, because we've got an amazing space industry here in the UK that's rapidly growing. And we're looking at more launch sites across the UK. We had a successful launch from Spaceport Cornwall. Although it didn't go to space, I actually said it was successful because the moment that 747 lifted off the runway, that was success. We have a spaceport in the UK that can launch a space vehicle with the regulation, with the satellite integration, with everything in place. And we're going to have more spaceports around the UK this year and into next year. So that's really exciting for the UK space industry as well.
Yeah, absolutely. And just getting the opportunity to go somewhere in the UK and watch something launch. In the future, we're going to be able to, maybe not quite the rocket I can see behind you, but we're going to be able to, access some of these places and be able to watch launches. And I think that's going to be a real game changer for people, because really brings it home, doesn't it, to have this on our own soil.
It's going to be so inspiring.
Sorry, I interrupted you there. We're going to have to wrap up, actually, because I'm running over. I could chat to you all day, Tim, but I'm afraid we have to go and find Fran, who is chatting with one of the schools that's here on site. Tim, if it's okay with you, we're going to come back to you in 5 or 10 minutes. Please send your questions in for Tim. I know this thing is going crazy, buzzing with questions that are pouring in right now. I'm going to try and collate some of those because there'll be far too many. And we'll come back to Tim and I'll ask him some of your questions in just a few minutes. Well, let's go over to Fran now and see what she's up to.
Tim is always full of such good nuggets of information, but this isn't just about meeting the superstars of space. It's about you guys getting involved with activities. And if you follow me, we have a school right here at Mission Control who are doing activities just outside of here. And they've been beavering away doing lots and lots. There's so much buzz coming on. And we hope that you are doing activities at your school as well. There's so much you can do, and if you haven't got activities together, you can just go onto our website and download some activities. And as you can see, there's so much going on, but I'm going to head right over to the back actually, and we've got drones and we're going to be coming back and looking at those, but we're going to head right to this far corner over here. And here, what is happening is an activity that's actually by the Mullard Space Science Laboratory. And what they're doing is they are replicating PanCam. Now, PanCam is a camera that will be on the Rosalind Franklin. That is the mission that's going to go there. And how are you guys getting on? Are you doing okay? And what is it that you're doing?
The filter we order is the same as the Mars Perseverance rover. Then when we're done, we use the different colour filters to look at different images.
Got you. So they're cutting out different circles and making a camera which then they'll put different filters on, just like there will be on the rover. And then by using the different filters, what you can do is you can see different aspects of the surface or different compositions of chemicals. And through using the different filters, different scientific information can be gathered. And so they're making a replica of that. And how are you finding it so far? You getting there? Brilliant. And if you head over here, there's another activity going on. There's so much out. I think there's drones stuck underneath the bookshelf. Oh. I think it's safe. Let's try. And we're going to head over to here. So yes, that one was about a camera, but also we need to be able to get samples from these planets like Mars, not just images. And so over here, we're looking at how difficult that is. And so, is it Sam, yeah? No, Luke. We've got Luke here. And what he's doing is they've got, what are you doing? Is that like a robot arm?
Yeah, it's meant to be a robot arm. Yeah, it broke.
It broke? Well, that does happen.
Yeah, it's been stretched quite a lot.
So this is a replica of a robot arm, and you're trying to operate it to get the ping pong ball from the cup into the sample bag. And this just shows you that it's not that easy to be able to make the machines that can do this, because these machines aren't in the hands of the scientists and engineers. They're up there in Mars, and so having control of them is no easy feat. But they're managing to do it, just like these guys are managing to do it. And how are you two getting on?
Doing alright, actually.
You're doing alright? Oh, don't famous last one. And if you tried different lengths of the arm as well?
Yeah, I found when it goes longer, the weight, like this.
Yeah.
The weight brings it down, and that
Yeah, it will do because of that moment, that pivot force.
that can cause it to like weigh down, obviously bend, and it won't be as effective. So sometimes the shorter the better.
And so it's sort of that balance, I suppose. If you're up on Mars, it's that balance of having a long arm so you can get lots of things, but they've got to be light, or a short arm so you can get, things that are closer to you, but perhaps can be heavier. So there's always that balance between the design of doing this. And these are activities that you can find online. There's so much going on, and we hope your school is just as hectic as here, with drones getting stuck in shelves. And are you enjoying it?
Yeah, yes, great.
It's brilliant, brilliant.
Better than school.
Say again.
Better than school, I'd say.
Better than school now. Could you get it? I like that compliment. I think it's probably time that we head over for more questions with Tim, and hopefully Susie is there, but we can go and check. Let's have a look. Is she there? Here we go, I'll leave them to it. And we are, let's see.
Time left. Ask this, what is it like to be orbiting the Earth and looking down on the Earth? Like the first time that you were really able to look back down, kind of what emotions did that bring up in you, and how did it change your sort of perspective on what it's like being down here on the Earth's surface? I got.
Hey, can you hear me?
There
okay
we go.
now?
Now I can hear you. Perfect.
There we go. Excellent. Yeah, the first time you look down on the planet, it's a mixture of emotions, because actually it's just after the engines cut out from inserting you into orbit. You've just been through this really violent launch process, and then everything is peaceful, beautiful, quiet, and you're just floating there. And you've been immersed into this completely different environment, and because you've had to go through such a violent launch, you're very aware that you're in a very strange environment looking down on Earth, but it's absolutely stunning and beautiful. And we actually ended up straight into night over the Pacific, so everything went completely black, and then the stars just came out, and you saw the Milky Way rise. Like I've never seen it before, hundreds of billions of stars, no light pollution, and then the moon came up as well. So it's absolutely mesmerizing. Planet Earth is such a beautiful planet to look down on. It really is.
And I guess that never gets old. You have the sort of cupola, this area with glass on that helps you. Do you have time to go and spend time there, just gazing at the Earth?
Oh, you do, yes. In a 6-month mission, you've got plenty of time. When you first get on board, life is really busy. I'd say probably the first 3 or 4 weeks, you're so busy learning just how the space station works, learning how to use your body in weightlessness. We had a spacewalk after just 5 days, where Scott and Tim had to go outside and repair a part of the truss segment. So life is really, really busy. But after a month or two, you get into the swing of things, and you start to kind of settle into life and work on the space station, and you can really carve out time for yourself to go and enjoy that cupola window and take photos.
So I have a question for you, actually, because I study the aurora, the northern lights. We see them in the north and the south, these beautiful lights that happen in the sky. And I've traveled many times to try and see the elusive aurora. And whenever I go, they seem to vanish and there's nothing to see. And people might be aware of this because last week there were beautiful auroral displays across the UK. Were there anywhere you were, Tim? Did you get a chance to go and have a look?
I looked out. We didn't see any. I was right in the south of England, so I didn't see it. But I've got lots of friends and family in Scotland, and they were being treated to some amazing displays. So I was very envious of the photographs that were coming back from them.
Yes,
but I did get to go to I got to go to Iceland last year, and that was the first time actually that I've seen the aurora from underneath it and not above it.
Yeah, well, that's what I was going to ask you about, actually. And as the sun gets more active, we might see more auroral displays over the next few years. But you got to see it from above, presumably, and that must have been quite different.
It is, yes, and it's amazing how it links together over the whole of the northern magnetic pole and southern magnetic pole as well. And you see it on this vast scale. It's like ribbons of green light, like sort of curtains, somebody waving them in the wind. And it's absolutely magical. It's the most sort of ethereal view that you could possibly imagine there. And what's surprising is the solar intensity increases, the aurora stretches up, and it goes from green to this reddish tinge on top. Yeah, I think it's just remarkable. It shows how dynamic our planet is, how vibrant it is. And, you know, with that lovely shot of Mars in the background, you realize, gosh, yeah, how different Earth is to Mars today, with everything protecting it from its magnetosphere, from its atmosphere that supports life, its weather systems, its storms, lightning, everything. It's incredible.
No, absolutely. We were talking slightly earlier with some people from ESA and the UK Space Agency about what happened to Mars, why it may have started looking like the Earth and why it looks the way it does today. And I think there were lots of questions about that. But for you, there were a lot of practical questions, actually. I'm just going to ask you a couple of those. People are very interested in what you were eating and actually, you know, how you go about kind of making a menu. Do you choose what you eat? Does someone test to make sure that you actually like the food that you're about to eat for 6 months, or is it just potluck?
We have a set menu, and it's quite varied, actually. We do get to taste it all before we go into space. So we can, if we like something, we can order a little bit more of it. There was when it came to green veg, you know, none of it's really that good. It's all rehydrated, but creamed spinach I remember liking quite a lot. So I kind of doubled my order of creamed spinach, so I could at least get some good healthy greens down me and some iron. But yeah, so we've got this set menu, and then what we have is 10% of bonus food, and the bonus food are things that we can quite simply go and buy off the supermarket shelf. Anything that you see that is that's got a long shelf life, and it's got packaging that's robust enough to, you know, for the launch up to space. The NASA and the food laboratories will take a look at it and either say yes, we can fly it, or no, we can't fly it. So it's mostly dried goods, and that's great. That gives you that kind of 10% of your bonus food, and also we can have some canned food as well. Often as European astronauts, we try and have some European food flown up to us just to kind of boost morale when you're on board the space station, because the space food is not really that great.
Well, I was thinking about food as kind of a cultural thing. It brings everybody together. It's kind of a highlight, I guess, if you get to have a treat. It makes quite a difference, doesn't it? And I saw an article that you worked with some real top chefs to design things like a bacon sandwich. Is that right? You have your own special Tim Peake bacon sandwich, everyone's favourites.
We did. We turned it into a competition. So I kind of handed over my 10% of the bonus food to a competition where we said, right, design a healthy astronaut meal for a day that's going to have all the calories I need, all the minerals and nutrients and vitamins, that can be low in salt, because it's important not to be too much high in salt, and all this criteria. And they entered the competition, and we ran it with Heston Blumenthal. And he had agreed that the winning team would get to go to his development kitchens and actually cook their meal for me, and it would get flown to the space station. In the end, there were so many entries and they were so good that we picked 5 teams. And so these teams all went to the kitchens there with Heston and his chefs. And it wasn't just the bacon sarnie. We had sausage casserole. We had a salmon dish in there. We had a chicken curry. We had some key lime pie. It was brilliant. And it really was the best food on board the space station. I'm convinced of that.
I love that you took that risk. I'm going to take my precious small quantity of food that I can choose and let somebody else decide what that's going to be. That's great. That's great. Again, so many questions to ask you, but I think one of the interesting ones when we think about the structure of our day is lots of people asking what you did before you went into space, and maybe talk to us a little bit about your career, because you had quite a fascinating career well before you became an astronaut.
Yes, and perhaps not a traditional path of becoming an astronaut. It was in the sense that I was a military test pilot. You might think, well, that's really the obvious route to becoming an astronaut. But in terms of school, I left school at 19 after my A-levels. I didn't do particularly well in my A-levels. That's not an excuse for anybody listening to not study. Actually, it's far easier if you do well in your exams. It makes it easier later in life. I did it the other way around, and so ever since I left school, I've been studying extremely hard. And I joined the army as a military pilot, and I flew on operations all around the world. I became an instructor pilot because I loved flying so much. I wanted to teach people how to fly, and then I loved flying so much I wanted to actually help to design and build the aircraft, and so I became a test pilot. And a test pilot is really a license to do absolutely anything you want in an aircraft. So it's a huge amount of fun, but we do it in a very controlled manner. We do have to take a lot of risk, but we make sure when we're doing that in aircraft that we know exactly what we're doing, why we're doing it, and how to do it. But you end up pushing the envelope of aircraft, trying to see just how high they can go, or how fast they can go, or how much weight they can carry. So I love the science behind that. I loved getting into flight dynamics. I got a degree in flight dynamics, and that's really what set me up to becoming an astronaut when the European Space Agency had their selection process. But there are so many different routes to becoming an astronaut. All of my friends have picked different routes. We've got some scientists, some engineers, we've got some school teachers, some computer programmers. We've got people from all sorts of backgrounds who have now joined the Corps.
Yeah, and presumably, actually, although we often see you and your fellow astronauts at the heart of our discussions about space, there's a lot of people behind the scenes that support what you're doing, that have a range of different careers. So it's not like astronaut is the only one. There's a lot of people in the European Space Agency supporting you, right?
Absolutely, astronauts, you know, the most visible part, if you like, of that team. But no, that you're absolutely right, Susie. There are so many people, and there are so many fascinating and interesting jobs to do. Before I flew to the space station, I got qualified as a Eurocom at mission control. This is the person who speaks to the space station. And again, working with all the people on the ground, the scientists, the engineers, the people in operations who keep the space station running 24 hours a day, 7 days a week. And so it's a truly exciting area, and that's just human spaceflight. No, we haven't even touched on some of the space science missions, for example, or the Earth observation missions, which are doing so much for climate change. I mean, the list is endless in terms of the number of exciting careers that are out there.
We have to wrap up shortly, and we're going to go back to Fran in a moment. I guess I have one more question to you before we do, which is, what are you excited about over the next 10 years, 15 years of you could pick one of 1,000 things, but it could be human exploration, could be robotic. What is on your mind? What are you looking forward to seeing happen?
Okay, I could speak for hours on this subject, but if I was going to pick one thing, it's seeing the first human walk on Mars. That has to be the most exciting thing. Before we get there, of course, we're going to see humans return to the moon, which is going to be incredible. We're going to have lunar bases, lunar laboratories. It's going to be exciting as well. We're going to have science missions go further out into space. We're going to see some brilliant imagery from the James Webb Space Telescope. We're going to learn more about the potential sources of life elsewhere in the universe. I mean, the list goes on and on and on. But if you just said one thing, watching that first human step down onto Mars.
That is an excellent answer. Thank you, Tim. And just the way you responded, your excitement just shows us, you know, how much there is to look forward to. Thank you so much for joining us today. I think we're out of time with you, but we really appreciate your time. Thank you again for coming on another Mars Day, and we look forward to you joining us next year. Fingers crossed.
Thank you, Susie. Great talking to you. Thank you, Fran. Take care, guys. Bye-bye.
We are going to go to Mars, figuratively. We have a little video to play you about the way that the Perseverance rover is operated on Mars, and Ingenuity, little quadcopter as well. So we're going to go and hear a little bit about operations on Mars right now.
Hi, I'm Sophia Mitchell. I'm the Deputy Lead Rover Driver for Mars Curiosity. I also worked on Mars Perseverance rover on the sample caching system. Welcome to JPL.
My name's Carrie B, and I'm a rover driver for the Curiosity Mars rover, and I also work on the Mars sample return mission on the twin helicopters we're about to send to Mars to retrieve the samples left behind by the Perseverance rover. In the past, I've also helped fly the Ingenuity Mars helicopter, which was the companion Perseverance rover, and I've also worked on the Spirit and Opportunity rovers. Welcome to JPL. Welcome to JPL's Mars Yard. This is where we test a lot of our Mars rovers and other robots. Before we send them to another planet, we do a lot of testing here to figure out how we're going to use them. Let's go for a tour. One of the things we do here in the Mars Yard is we do a lot of practice runs where we can test driving our rovers here on Earth before we send the commands to Mars. One of the things that's really scary as a rover driver is sand. And so we have this pile of sand here. We can change the slope. We can do a lot of practice driving up and down to see how our rover is going to perform when we're testing over sand. And behind you is a whole bunch of other rock slopes that we can use to do a lot of testing. So we have a whole bunch of different materials, and we have a whole bunch of different slope angles. So when we have new rover drivers come along, we actually have them come practice seeing what the rover is actually going to drive like here. And so they build that intuition, because you can look at it in a simulation, but the simulation is going to think it's perfect. When you're at a 20-degree slope on sand, it's going to be much different. So that's part of the reason we have the Mars yard set up the way it is. So this is an example of one of Curiosity's wheels. So you can see we've got this kind of chevron pattern on here as a tread to help us climb over rocks and drive around. We also have in Morse code here the letters JPL for our place, Jet Propulsion Laboratory. And the reason we have these is to help the rover drive. So we're planting this on the ground, and so if the rover needs to track its location, we can actually use these features to help us localize the rover. And one of the things you'll probably notice is these wheels are a bit banged up. And so we've actually found this is happening on Mars too. So a lot of the rover driver techniques are actually to slow down how the wheels are breaking apart. And we've done a lot of work, and the wheels are doing great now. And so we've been able to use a lot of the lessons we've learned here to inform the next rover, Perseverance's wheel. So this is an example of Perseverance's wheels. So you can see they look quite different from Curiosity's wheels. So they still have a tread mark, but it's not the chevron pattern that Curiosity wheels have. They have just a slight wave instead. This is also based on the terrain difference, that Perseverance would be kind of climbing out of the delta, whereas Curiosity would be driving around, climbing up a mountain, but with different types of terrain. You can also see that they've removed the JPL Morse code for the visual feature. They found we weren't using it that much for Curiosity, so to save on complexity, they were able to remove it and make Perseverance's wheels different. One of the other things is this one's a little bit more narrow than Curiosity's wheels, so they were able to make the wheel a little bit thicker and make it a little more narrow to help reduce the amount of damage that we were seeing. So now that I talked about the wheels, you can actually see how they look integrated onto the rover. So in the front here, you can see part of our suspension system. So this is called the rocker bogie suspension system. So the front here is considered the rocker. And so this helps keeps the rover stable and flat as we're driving around on the terrain. So as this wheel pushes down, that one on the other side would push up. And so it helps keep the rover stable. In the back here, the wheels can move more freely. The back section here is called the bogie. And so this can more freely go over the rocks that we drive over to help keep the rover stable as well.
This is Maggie. This is Curiosity's twin. So every time that JPL builds a rover to send to Mars, then we also build a duplicate rover to keep here on Earth. So part for part, Maggie is exactly the same as Curiosity on Mars, except its power supply. So Curiosity uses nuclear power, and obviously we can't have a nuclear power supply in the test bed. It wouldn't be safe for us to be around. So that's the only major difference between the two robots, but everything else is the same. The reason that we do this is because when we're trying to develop new capabilities, or if something goes wrong and us rover planners and engineers need to fix it, then it's a lot easier to fix it here on Earth and then send that solution to Mars than it is to try to troubleshoot on Mars. So it plays a really important role, especially when things go wrong. So looking at this rover, Harry covers the wheels, but we've got the robotic arm that's all tucked away and stowed, so it's nice and safe for driving. And we've got the mast here, which is what looks to most people like Curiosity's face. We also have some instruments on the top of the rover that I'll talk about in a moment. So the robotic arm is what's called a 5-degree of freedom arm, which means it can move in most directions, it just can't twist its wrist like you can. It has a bunch of instruments on the end that help scientists and engineers work together to figure out what the rocks that we're finding on Mars are made of. So we've got a drill, which we use to get samples of the rocks and put them into our instruments. We've got what's called APXS, which is that curved plate you can see, and that gets placed on rocks, and we can get some composition information from that. There's also this square hole you can see that is actually a sieve system, so it sorts the rocks by size, and then the portions come out of that portion there, the hole there. There's also, one of my favorites on the back is Molly. You can't see because of how the arm gets sewed, but that's our little camera on the end of the robotic arm. So when Curiosity takes selfies, it's actually taking a series of 50 photos using that camera on the robotic arm, and that's how we did this. So I mentioned that when we drill, we get sample that either comes out of the portioner or now we get it directly out of the drill. We put it into these instruments on the back. There's one called STAM and one called ChemIn. And each of those instruments does something slightly different. One bakes the sample so that the gases coming out of that rock can then tell us what that rock is made of. And the other one shoots X-ray particles at the sample. And then based on how those interact, we can tell what the rock is made of. So it's truly a Mars science laboratory. Finally, we have the mask, which I mentioned before. The big red circle on the top is our laser. We get paid to shoot lasers at rocks on Mars. Coolest job ever. When it shoots that laser, it again looks at the spectra of what comes off of those rocks to give us some idea of what they're made of. We also have the mass cam and navigation cameras, and those take the color and black and white images of the Martian surface so that rover planners can use that to decide where to drill, where to place all the tools of our robotic arm, and also where to drive. So like I mentioned, one of the reasons why we like to have this test bed here on Earth is so that when things go wrong on Mars, then we have a place where we can work together to figure out how to solve the problem before we do it for the first time on a different planet. One of the main problems that we've run into on Curiosity was the feed mechanism breaking while we were trying to drill. So what that mechanism does is, traditionally, the way it was built, the drill would be stabilized against a rock before then the feed mechanism would feed the drill bit assembly down into the rock to drill. And in 2016, while we were trying to drill, that mechanism broke, and so it got stuck. So part of the problem was, how do we get unstuck so that we can push our drill all the way to the end of its feed, so then we can have it fully extended? And the other question was, how do we drill again on Mars? We can't send someone up there to fix the rover. We can't go get it and then send it back. We had to just relearn how to drill in a way that the system wasn't designed for. So this is a drill bit assembly. We have multiples of these. The rover actually on Mars has 2 additional ones it can pick up. And the way that this works is it's hollow. And the rock, as it's getting crushed up into tiny bits, goes up the stem and into the chambers. And if we want to get that rock back out, it can either come out this port or come out the other end of the drill.
From Kerry and Sophia there, and they'll be joining us for a session this afternoon at 5:45. But I'm quite excited now because we're about to go through and see Egglescliffe School doing more activities and maybe find out what those drones are all about. So over we go. Let's see. Oh, there's a pillar there. Gosh. Okay, they're not up in the air yet, but maybe. Okay, how's it all going on? How are you getting there?
It's going well. We're just waiting for program for
So that one's yours up there, and you've made a program on here to fly the drone?
Yeah.
Fair enough. And this is the Mars. This is a Mars map. And so are you attempting to fly it instead of? Did you just flip it? So of course, so it's an automated program. So once you've made that is fascinating. So they're making an automated program for the drones. And if you, is it landing in?
Landed.
Oh, is it landed? Is it landed the way you wanted it to?
Yeah.
Hey! See, they just need these people to do it, and it will be fine. So did it take you long to put the program together?
No.
Yeah, it's the block coding, isn't it? Yeah, so that drag and drop coding that you might be used to, where you just drop in a block, and so that's quite simple to use. And so what have you got your eye on next? Which location? Olympus Mons, aiming high, only the biggest volcano that we know of. Gosh, so you're going for Olympus Mons, right? And we've got one here. I feel like we might have to duck at some point. Let's go over here and see how we're getting on. You just landed, didn't you?
Yeah, do you want me to zoom it again?
Yeah, we can see. Like, but did it land where you wanted it to?
Yeah.
Hey! And are you enjoying it?
Yeah.
Brilliant. So is it running your same program again?
Yeah, it reads the program and then we tell it to flip and then it tells us for 257 years.
Yeah.
It just put that flip and then lands.
Brilliant. Hey, and it'll work. Perfect. Gosh, so what they're doing there is they're putting in automatic programs. So what they've done is they've programmed it to go up a certain height and then flip and then land back down, and it worked exactly how they hoped. And what they've got here is a giant Mars map, as you can see, and so they're aiming for specific locations. And these activities, I know that this activity Ecclescliffe School has come up with their own in terms of with the drone flying, and you can come up with your own activities for Mars Hour. It might be a bit late for this year, but you can totally do it for next year. And the other activities that will be going are ones that are available on the website. And there's loads of resources for you to do things. And there's loads of stuff going on, not just for Mars Hour and not just for Mars Day, but also for Mars Week. But I think it's about time that we go back and join Susie in HQ, and let's see what she's getting up to, because I think she might have a little activity that I need to do. I don't know how I quite feel about this, but we'll see what happens. Okay, in we go. Oh, I had a lot of fun out there, and we didn't get hit by a drone, which is quite nice. It's always good. Okay, are you here, Susie? She is. What's she got for me to do? Oh gosh, Susie, I heard you've got an activity for me.
I do. You were just flying drones around.
I was watching people fly drones.
Well, this is your opportunity to dive right in. So,
okay.
A Mars rover. This is a composite image of the Gale crater taken by Curiosity. So actually what Mars looks like, and that's what we have on the ground here. We've got a few obstacles.
Yes, you have.
We've got a rover and we have a controller.
Oh gosh, right.
So your job is to, let's sort of drive around, see if we can get over that bridge down there. And you can tell us a bit about why this is challenging.
Okay. So this must be right. Let me. First of all, I've got to figure out what each control does. So that one. Well, they do say it takes 20 minutes, don't they, for the signal to get through to the rover. So we'll see. What about this middle one?
We haven't got that much delay programmed into this, but that is one of the interesting challenges to think about, isn't it? The fact that the time delay with the signal.
Yeah, and it must be so tricky as well if you're like putting in what you want it to do and then having to wait for it to respond and then seeing what that response is, because of course there's also going to be a delay in the signal coming back of its response. So let's see. So at the moment right on cue. Okay, so that takes it back.
Yes, I'm so sorry.
Spoke too soon. And I think there you go.
So this thing is pivoting in the centre. Yeah. Good. So how good are you at reversing? What is your driving level?
I don't have a great track record of reversing. I've got to be honest with you. But you know, I can learn. Okay. This is the articulate bit in the middle. Articulated. Right. And this is the problem, I suppose, when you're putting in controls, is you go like, oh, that one hasn't worked, so I'll put in 10 more. And then it tries to do it 10 times, then you can overload the system. So I guess this is very much a model, isn't it?
Absolutely. But in fact, yes, so this is of course a little Lego model here, but what we do have around the world are sites that are analogues for Mars. So we have various regions, both in laboratories and actually outside, that we think are analogues for the Martian surface. And so what we can do is train people in how to do things like this on a Martian analogue. So perhaps with a soil type that's very similar to the soil that we might see on Mars, with prototype instrumentation that we might be sending to Mars. So we can really test what the environment is going to do to it. So we haven't got far yet, I have to say.
To be honest, I'm not sure this is my future career of driving these Mars-bound robots. It's a good job we have people, you know, like Susie, to help us.
No, I have a terrible track record of Mars rovers. There's a really good reason why I've asked Fran to do it, which is that I have had a go in one of these Mars rover prototypes and wasn't terribly successful.
Okay, so. We had a bit of movement there. And when we were talking about, so obviously this is a model of the robot and the rover. But in terms of the models of Mars, yes, you were saying that you can have surfaces that are on Earth that are like it. But I know that Sue was talking about models of Mars. And what did she mean by that? Did she mean physical models or like digital models?
We have both. So we have lots of images taken by orbiting satellites and indeed by our rovers that come back to us that help us understand what the surface looks like. Obviously, the rovers are taking images of a small area in lots of detail. The orbiters are looking at larger areas from orbiting the planet, so slightly different there. So we can certainly build up a picture of what we expect the surface to look like. But as Sue mentioned, when we sent the Ingenuity lander to Mars and it was meant to drill, it had some issues with drilling. And some of that was associated with the differences between the conditions that the rover discovered on Mars and our expectations. So every time this happens, we learn a little bit more. And we are hopeful that we gain information and the next drill that is designed will be successful. And indeed, we've been discussing that next drill, which is on the Rosalind Franklin rover, hopefully to launch in 2028, designed to dig down 2 meters to bring back samples, or to analyze samples actually, from under the surface of Mars. And that's important because, as Sue mentioned, the surface has been exposed to high doses of radiation, and we want to see samples that haven't been exposed in that way. So actually, you've done a good job.
I'm doing
here.
okay. Like,
Yes.
I'm not doing excellent, but it gets me thinking in terms of, because here I'm controlling it, you know, I put in the signal and it goes straight to it. But you can also have autonomous robots, can't you, where you pre-program them and they do what you said. And that's what they were doing out there with the drones, where they were pre-programming them and the drone was following that program.
Absolutely. And in these conditions where there's a time delay between your signal and the response of the vehicle, one of the things that's quite important to do is have recognition software on board that recognizes a hazard. You want this thing, as it moves along, to be able to recognize that there's something coming up that's hazardous to it and to stop and wait for command. You can't just expect the driver to be able to see that coming and react in time. As we mentioned, some of the time delays of the order of tens of minutes. And so yes, part of the skill seem to have come to a
Is that a signal again?
Part of the skill is developing autonomous vehicles that recognize danger before they reach it and are able to respond appropriately. And actually, as we explore further out in the solar system, as we head further out, thinking about, for example, landing on some of the icy moons, Europa, etc., we're going to have to develop more autonomous vehicles because we're not going to be able to drive these things directly or operate them directly. The time delays are too big. We're going to have to program them and have them understand the environment.
And it's really interesting because you say the time delays up in Mars are quite significant. You know, I'm having trouble here. But what's
Yes.
interesting about those autonomous robots, it's not just a case of pre-programming and it's saying you land here, you know, go forward 3, go right 3. It's saying, because that means you've got to get the landing completely right. What you're saying is actually the robots, in a way, they have a bit of, I suppose, intelligence themselves, and so they can look at the environment of where they land, and so they're not just trying to bash into a rock repeatedly.
No,
they can actually work their way around it.
Yeah, and then the Martian environment is such that actually there are regions where if it was to drive into a region, it might be very difficult to get it back out again. So actually they're very careful with their asset, which is very expensive and it's taken a long time to get there. Very cautious about how it operates. And yeah, exactly, this disaster recognition is really important.
And I suppose especially if I'm driving.
I don't think you're going to get a job driving the next one, but I did enjoy that. Thank you.
We are having a lot of fun here, not only with the activities that the schools are doing, but the activities that we're doing. And a lot of fun has been had doing activities in the past, as we can show you, because there's the European Space Agency Hackathon, which happened. And we've got a video to show you that just now.
We've got a case on our hands. 2 mysterious exoplanets, and we need to profile them.
This looks like a lot of work.
Are you thinking what I'm thinking?
Let's hack an exoplanet. Hi, I'm Katya.
And I'm Ali. We're from ESA Education.
We need your help to investigate these exoplanets, some of the oddest planets orbiting other stars in our galaxy.
The European Space Agency developed satellites that study exoplanets. One of those satellites was called CHAOPS. You'll hear more about CHAOPS in a little bit and how you can use its data. Yes, you heard me right. You'll use a satellite's data for your very own school project.
Are you ready to be a space detective and hack an exoplanet? Data we collect with satellites are like fingerprints. At first glance, they all appear very similar, but if you look very carefully, you can identify certain characteristics that are unique to your exoplanet.
In early 2023, we're going to point CHAOPS to 2 exoplanets, unlike anything you've ever seen. Target A will be the giant Kelt 3b. This exoplanet is unlike anything we have seen in our solar system. It's a large, puffy gas world orbiting very close to its host star. It's even bigger than Jupiter, the biggest planet orbiting our sun. And because it's so close to its host star, it's very, very hot. In fact, it's so hot on this planet that there are some stars where it'd be possible to go to cool off. We call these hot, gassy planets hot Jupiters.
Cheops will then turn its eye towards target B, the almost tropical TOI 560c. Compared to Cal 3b, TOI 560c is almost tropical, though still too warm for we humans to go there for holidays, since it's still hundreds of degrees Celsius warmer than Earth. This youthful exoplanet is over 2 times the size of the Earth, and we believe has a similar internal structure to Neptune. Because of these similarities, we call this type of exoplanets a mini Neptune.
Now, we want you to use your detective skills to investigate these 2 targets by joining the first ever ESA Education Hack an Exoplanet event in April 2023.
During the hackathon, you will analyze data from Cheops to profile our 2 mysterious exoplanets, Cal 3b and TOI 560c. The hackathons will be hosted online as well as in participating schools and other locations.
Which is your favourite planet? Cast your vote for the winner. Will it be the giant Kelt 3b or the almost tropical TOI 560c?
Head over to hackanexoplanet.esa.int to vote and become an exoplanet detective. Complete the quiz and other activities to receive your badge. In the meantime, we'll be busy. Cheops will observe the targets and collect data for you to hack.
Be sure to cast your vote by February 2023. Stay tuned for more information. See you soon.
Brilliant. As we said, there's loads of activities going on, not just all for the next 5 minutes, so Mars Hour, but also for Mars Day and for Mars Week. So